Hi guys, and welcome to grade 12 trigonometry. Grade 12 trig is essentially consolidation of all the trigonometry you did in grade 10 and 11. And then having consolidated, we just extended a little bit. So I'm going to start right away here with the derivation of the first compound angle that you guys encounter. And from this compound angle, you are able to bring the many other compound angles. Maybe one thing just to uh, set you up. At this point, you guys should be very sharp with the cast rule. All students take care and try setting up triangles therein. And you should be very sharp with general solutions, the 5 types or 4 types that you get, if you like, and the trig identities, and also some restrictions on identity. These are very key fundamental concepts that you need to be very sharp with so that you can cope with what we will be discussing in the grade 12 level geometry. And if you feel you need to recap a little bit, I'd encourage you to just have a sneak peek into the grade 11 series of trigonometry that I have compiled. It's already up. All the topics are there, of course. I've not yet put up the sine and the cosine rule, but they will be there soon, and you'll see them once they are up. Now, we whatever we're gonna learn here, let me make this very direct and straight, so that you take it seriously as well. Whatever I'm going to discuss here, I hope you're checking out. You're probably asking yourself, what is this? But you should know by now, there's the unit circle. And the unit circle and the functions, in other words, the graphs of trigonometric ratios, actually rather trigonometric functions, they are very key to us as students of trigonometry, because they help us to understand or come up with shortcuts that we can use, for efficiency. So you will see from this one compound identity that I am going to derive with you, we will derive many other compound identities. There's at least 4 of them. And then we'll do the double identity also from this very same thing. And I will end this by discussing the half identity with you. Now, whatever we are learning, all these identities that we're going to learn, you are going to use them for general solutions. You are going to use them for proving identities. You're going to need them for simplifying trigonometric expressions that involve special angles, non-special angles, half angles, non-numerical angles, where maybe they just say alpha plus beta or 2 alpha plus beta, something like that. And even in 2D and 3D problems, okay? Guess what? You will also need to solve them, to use them rather, when you do functions, especially where questions like find solutions for the graphical solutions for this equation, stuff like that. And so even in incorporating the sine and the cosine rule, you will need to understand these identities. I cannot stress how important these identities are, guys, than to tell you that they are in every component of trigonometry that is going to follow. Hence, we start with them. All right, enough said. If you look at my triangle here, it's a unit, well, I've got a unit circle here, and I'm using a different approach to derive this. You might have seen it, you might not have seen it. And so the radius is 1, okay? As you can see, here is the 1. So maybe I should put this R here. So you can see everywhere that my radius is 1, okay? And then the next thing that I want you to pay attention to is my angles, okay? I've got an angle theta here, which is 50 degrees. So theta actually goes from this line here to that line, okay? That's my theta. And then I also have an angle called beta. So beta actually ends somewhere here. Then I've got an angle called alpha, which ends somewhere here. Okay, now what I'm doing here, I'm finding the difference between alpha and beta, and that difference I have named it delta. Here is delta. You can see it is 50. 50.5 and theta is also 50.5. In other words, delta, okay, delta, which is basically the difference between alpha and beta, is theta. That is a very important note. Now, I've got certain x values here, okay, and y values. And you remember this is x, that is y, this is x, and that is y, that is an x coordinate, and this is a y coordinate. Now, what is sine? I think by now you know this as grade 12s about SOHCAHTOA. I don't need to talk much about it. So you know that the sine of theta, for example, sine of theta. Now, in this case, I am actually not going to say sine of theta because theta is alpha minus beta. So I'm going to say sine of alpha minus beta. Okay, what is sine of alpha minus beta? It is y over r. Okay, so y over r, but r is 1. So therefore, we can just see that actually the y coordinate is the same as sine alpha minus beta. Okay, the same thing, guys, happens for cos. If I say cos alpha minus beta, this is going to be x over r, but we know r is just 1 because there's the unit circle. So the x coordinate here is just cos alpha minus beta, right? And then what we now going to do is, instead of having that there, I'm going to write this coordinate in terms of sine and cosine. So this coordinate here, guys, is actually, because it's the x value, we're gonna say is actually cos alpha minus beta. And this coordinate here is sine alpha minus beta, okay? Now, the same idea applies here. So but in this case, we are reasoning in terms of beta. So the x coordinate here is cos beta, okay? And the y coordinate here is sine beta, okay? In the same respect here, we're using alpha. So the x coordinate here is cos alpha, and the y coordinate here is sine alpha, right? Now, I'm simply going to apply the distance formula. But before that, let me make you notice something. This side here is 1. That side here is 1. The same thing in this triangle. In other words, now I'm challenging you to look at triangle. You see that coordinate there is C. So the center is O. Look at triangle COD. Compare it with triangle AOB. So you see this is side. This angle we already saw it's 50.5. That angle is also 50.5. That side is 1 and that side is 1. If you remember your congruency conditions, we actually have side, angle, side. And so these two triangles are congruent. And the fact that they are congruent means this side here is actually equal to this side. And of course, this side is equal to this side, which is equal to that side and that side. So you see right away, it's very obvious. So we're gonna use the fact that AB is equal to CD to derive this important identity, okay? And think with me, if AB is equal to CD, then surely AB squared should be CD squared, okay? I mean, think about it. If 5 is equal to 5, then 5 squared should be 5 squared, okay? If AB is 3 and then CD is also 3, so 3 squared should always be equals to 3 squared. So that's irrevocable. We leave it there. So quickly, I don't want these videos to be too long, lest you be weary. I'm going to start with the distance AB, okay? So I'm going to start with the distance AB. And for that, I'm simply going to use the distance formula, which I believe you remember for you from analytical geometry. So AB squared, okay, is what? XA minus XB, or you could say XB minus XA, it's immaterial, and then plus, okay, YA minus YB all squared, okay? And then the x at A, let us look at coordinate A. What is that? It is cos, very important, cos alpha minus beta, okay? Minus, what is the x at B? It is 1, okay? This is squared. There's the coordinates for B. Plus, what is the y at A? At point A, it is sine alpha minus beta. But then the y at B is 0. So that's it. Now, realize I might just run out of space. So I'm going to move a little bit skew here. My equation sign will not fall off really underneath. So let's simplify the brackets. You're going to have cos squared alpha minus beta, right? Minus 2 cos alpha minus beta plus 1, okay? Plus, this is just sine squared alpha minus beta. But you know the square identity already that this thing here will give you 1, okay? So now you're going to have, here's your equation, you have 1 minus 2 cos alpha minus beta plus 1. So this whole thing actually then simplifies to 2 minus 2 cos alpha minus beta. Now I'm going to call that equation 1, right? That's it. Now allow me to wipe off here the top so that I can derive equation 2 and we just join the two equations together. Maybe I might leave that as an exercise for you to then prove the remaining results, okay? Now, having that said, we're going to set up equation 2 by looking for CD squared. So CD squared is, we now know, xc minus xd all squared plus yc minus yd all squared. And this here, what is x at c? X at c, we can see that will be cos beta. So that is cos beta. X at d will be cos alpha. I gotta square that. Y at c is sine beta, and y at d is sine alpha. And I have to square that. Now, if I do this quickly, I'm foiling, and I hope you can follow up that I square, and then I'm gonna have minus 2 cos alpha, cos beta, plus here I'm gonna have sine squared beta minus 2 sine alpha, sine beta, plus, of course, sine squared alpha. So that reminds me here, I actually forgot to add cos squared alpha, right? Yep. Now, check this. Again, we're going to use that special identity. Cos squared alpha, sorry, cos squared beta will merge with sine squared beta. And then again here, cos squared alpha will merge with sine squared alpha. Okay, squared alpha, right? Then that each of that will give us what? A 1. So that being said, I'm just gonna have a 1 plus 1 here. You know it comes from, okay? The blues are giving us a 1. The purples are also giving us a 1. So I'm now having that, okay? Minus. As a matter of fact, what I'm gonna do here, I'm gonna group this like terms. So you look at this. There's a 2 here, and there's a 2 here. So I can factorize. If I factorize minus 2, okay, actually, I'm jumping a lot of steps. So let me just write it down for you so that at least you can follow through here. So the 1 plus 1 is 2. So that's what I was saying. I'm going to take out the negative 2 here. Then I'm left with cos alpha, cos beta. I take out the negative 2, then I'm left with plus sine alpha, sine beta. Okay, this is equation 2. Now, as we have already established that if AB is equal to CD, then AB squared should be CD squared, okay? And we're gonna apply that. So again, guys, I'm a rub off here because of space. You'll pardon me, I don't have my whiteboard here because I wanted to illustrate this to you where we get this thing. There's another way you could do this, and that is to use the distance formula combined with the cosine rule, okay? The cosine rule, which you learned how to derive and use extensively, I believe, in grade 11. So that's another way you could do. You set up just one triangle also within the unit circle. So you see the unit circle is still key in both. I might just be in trouble here because I deleted my equation 1 and I did not write that down for you guys, but I remember it. So in your case, what you could do, you could just, of course, because you'll be watching this video, just rewind. Okay, so I know my equation 1. So let's see. We know that CD squared is AB squared. So what is CD squared? CD squared is 2 minus 2 into cos alpha, cos beta, plus sine alpha, sine beta. And what was my AB squared? I had 2 minus 2 cos alpha minus beta. I hope you guys remember that. Now, guys, you'll see 2 is positive here, 2 is positive here. Now, if a number or a variable is positive on both sides or has the same sign on both sides of the equation, you know it's going to fall off when you take additive inverses. So this 2 is going to take that off, and you are left with minus 2 of this thing into minus 2 of that thing. So again, if we divide by minus 2 both sides, everything falls off. Therefore, cos alpha, cos beta, plus sine alpha, sine beta is indeed equals to cos alpha minus beta. End of proof. That's it. That easy? Yes, it is that easy. So there's just a little bit of what you can say manipulation that we did there, but it's not really manipulation. It's an analysis, it's observation that is there. So remember, the lazy mathematician always comes up with shortcuts to solving sorts and sorts of complicated stuff. And so, like, once again, we are grateful for the lazy mathematician that here is a shortcut to solving a compound angles. And from this, I'm going to derive another identity. I'll show you how to derive the remaining identities using this very same identity that we just got. So we'll end it here for the introduction. I'll catch you later when we move on with deriving the remaining identities. Cheers.